Hello everyone, I'm Abhinav Rajiv Kumar, and today I'll be reading and explaining the paper Chain of Draft, where basically, as the paper says, thinking faster by writing less. So let's start off with the thing. Let's start off with what we did in the last video, wherein I opened up TLDraw and I'll try to explain everything visually and how everything works. But before we begin with that, we'd have, like I mentioned, certain papers which I feel you should read before you start reading this paper so that you understand it better. So, papers to read, let's start off with that. First, I would say, obviously, which is Chain of Thought prompting paper by Jason Way. You should read this paper to understand how chain of thought and chain of draft differentiate. That's one of the topics which I'll be addressing in this video as to how both of them differentiate and what are the advantages of using a chain of draft based prompting technique and chain of thought based prompting technique. Another paper which I feel you should read, there are two other papers that is. First is LLMs are zero shot reasoners by Takeshi Kojima. Takeshi Kojima, and language models are few shot learners by Tom Brown. So large language models are few shot learners by Tom Brown. So these are the papers which I feel you should read before we start off with understanding this paper. So this is the paper. I'll obviously provide the link of the paper in the description and also the link of the canvas over here, which we'll have where we'll be doing all the explaining. So when we first read the abstract, basically over here it talks about how they're going to differentiate between chain of thought and chain of draft. So over here they say, in this work we propose chain of draft, a novel paradigm inspired by human cognitive process. So it's trying to link how us as humans think with reasoning for obviously models. Like I mentioned in the last video, models struggle with understanding context or simple reasoning which comes to us by common sense. So that is something which large language models struggle with because they're made up of neural networks, right? So whenever you give them information, they're basically growing new nodes or neurons or something. We don't do that. As let's just take, we have a human brain over here, very badly drawn human brain. Whenever we gain new information, we don't just grow new neurons in our brain to store that information. It works in a different way. Whereas for a language model, it has to, if let's say it has two nodes filled with information and you feed it a bit more, it will have to go two more nodes. So like four nodes worth of information, and this multiplies maybe like square, cube to the power of 4, etc. So obviously, if you've been following large language models, you will understand the term chain of thought prompting. It's also known as COT. So it's basically, the way chain of thought works is you're asking the model to think step by step. So we have unlocked basically a reasoning process for a model to answer. You can kind of think of it as it's self-thinking. Basically, you're asking it to think step by step, right? But it's essentially how we as humans think aloud. The problem with this is, although it's effective, like let's take an example. We have a prompt saying, what is 9 to the power of 10? Let's say we have this. So we know that 9 to the power of 10 is something like 3 billion or something like that. I think it's 3 trillion, something like that. It's 3 billion. Yeah. So we know this, and we probably won't do 9 into 9 into 9 into 9 10 times, right? We're just going to probably put it in a calculator, do it 9 to the power of 10, and we'll just calculate the 3 point something billion. We'll just calculate it like that. But for a language model, it just can't input it into a calculator, right? It has to understand the task in hand. So it basically takes the context, that is, what is 9 to the power of 10? Now, in its data, or however a model is going to do it, it's going to do it in the simplest way possible, which is 9 into 9, and it'll understand, and I just need to do this 10 times, right? So this could mean that it's getting stuck in a recursive process, and that's the point which we are coming across over here. The point is that although it's effective, it's generating a ton of text for those intermediate steps which we are doing, that is the reasoning steps which we are doing. It's creating too much of text, and that does what? It uses up tokens, right? And if it's using up more tokens, we are going to come across two main problems, which is higher latency. That is where it's taking longer for the model to answer because it's thinking so much, right? And the second problem is higher cost. More tokens generated means more, you're paying more. Let's say if you're using like a paid model, you're going to pay more. And if you're using them at scale, obviously this 9 to the power of 10 was a very simple problem or a simple prompt where it probably won't even use reasoning for this. It'll just have a predefined answer and it'll just spit that out, right? For other tasks where it has to dig deep, where it has to actually think, that's where the higher cost actually comes in. So high latency, like I mentioned, takes longer to write the answer because model is like, let's say it's writing a novel. And higher cost is because more tokens are being generated. Okay, so generated. Okay, so we've gotten this point across. This is a problem which is there. Now, let's take example of like a very complex problem, something which will require lots of steps. Now, us as humans, we're not going to write down every single sentence, right? If I'm thinking aloud, I'm not going to write down, okay, so let's just assume you're taking a derivative of any simple equation, 2x squared. Let's take that. Let's take example 2x squared, we're taking derivative of that. I'm not going to write down what do I mean by derivative and what do I do, like what's the max which we'll do. We'll write down the general formula for calculating a derivative of this form, which is just na, right? The x cuts off and then this comes over here and we're just going to multiply it together, and that's our answer, which is 4x. Okay, I just realized that was okay, that's my bad. It's this is just going to come over here and it's just multiplication of this and it's x. So that's the basic formula, right? We're using the differentiation rule. So that is the max which we'll do, and we'll write down the final answer, which is 4x. For a model, this is not the case. It's going to write down every single sentence and it will write down everything to solve that equation. This is where chain of draft comes in. So over here, they mention that, let me find the page. Yeah, chain of draft prompting. Over here, if you go to this page, they're basically mentioning that, like I said, LLMs often produce lots of reasoning steps, which results in a sustainable number of tokens, or it consumes a lot of that. So they have proposed the novel prompting strategy called chain of draft, where it's aiming to limit the number of words used in each reasoning steps and focusing only on the essential calculations or transformation that are needed to progress, right? So let's take example of this question only. Jason had 20 lollipops. He gave Danny some lollipops. Now Jason has 12 lollipops. How many lollipops did Jason give to Danny? Let's take this over here. Obviously, we'll go back to the paper to understand how they have calculated it. But just to visualize it, we'll come over here because visually explaining things are usually much nicer, right? Okay. So the main problem over here is Jason over here has 20 lollipops and Denny has X, right? And over here we can see that now he has given, that is Jason has given Danny some lollipops, X number of lollipops. Now Jason has only 12. So how many lollipops did he give to Denny? Okay, yeah. How many lollipops did he give to Denny? So it's just simple maths. X is equal to 20 minus 12, which is 8. So he gave 8 lollipops to Denny. We did this in just 2 steps. If you're good in arithmetic calculation, you probably don't even need to write this step. You'll just write this answer right away, which I'm pretty sure many of us can do. An LLM, or especially on chain of thought prompting, is probably not going to be able to do that. It's going to write every single sentence down. Okay, so it will write like, okay, so I can see that Jason has 20 lollipops and he has given some to Denny. Then it will probably try to understand what the task at hand is. Oh, great. Okay. It will try to understand what the task at hand is. That is the a chain of action or the action which it needs to take, which it understands from the prompt itself. So the action plan which it will draft is, I need to calculate how many lollipops were given to Denny, right? So it will start doing this, and there will probably be lots of text over here. That is too much. What we are going to do over here is, with chain of draft, is we are just jotting down the important stuff, the key numbers, sometimes, or maybe the intermediate calculations which are required, right? So the key numbers over here is what? 20 lollipops and 12 lollipops. And the intermediate calculations would be, he gave Denny some, and the final answer, which is how many. This is what we're trying to calculate over here. That is what the chain of draft based LLM will probably do. To better understand how actually chain of draft might improve certain reasoning tasks, or is an improvement for certain reasoning based tasks, we actually have to understand how chain of thought actually works, right? So let's take this example only from the paper itself. We can take this example and we'll give it to Gemini. Gemini 2.5 Pro is a very well-known reasoning model, so we'll just give it to that, and we can see the thinking process over here. I need to find the difference between the number of lollipops Jason initially had and the number of lollipops he has now. The difference will be the number of lollipops he gave to Denny, initial lollipops now, and then lollipops given to Denny, initial lollipops minus lollipops now. Then the model has reasoned all of this, and it knows. Now it is starting to output the stream of the text, or output the tokens, right? So it starts off with, again, what we already know, because that's how a model is tuned to answer. Give the information which was given to you first to the user, then present your solution. So it talks about the details which has been given in the question, then it finally solves and gives us the answer 8. Now the same task over here is done with chain of draft. So over here we can see, let me just zoom in a little. Over here we can see that chain of draft is very to the point. Jason had 20 lollipops, the question is there, 20 minus x is equal to 12, x is equal to 20 minus 12 is equal to 8, and the answer is 8. The reasoning over here, like they said, is distilled into a concise equation, and it's focusing solely on the essential mathematical operation which is required to come to the solution. Now, a very famous or a very well-known question in the chain of thought world is the mathematical problem, or the coin tossing problem. So let's see how they address that over here. Where is it? Where is it? Okay, let me just search for it. Coin toss. Oh, coin. A coin flip tasks are introduced. Okay, maybe it's not in this paper. Okay, that's my bad. I thought it was in this paper. Okay, so let me just think of my own example which we can try to compare with. Okay, I've thought of a question. This is the code, by the way. We can check out the code also as to how it's actually working. So first, let's come over here. Let's change the color to red. And here's the question. Let's say Peter has 5 baseballs, something like this. Okay, and we can take, like, he buys two more. He buys 2 more cans, where each can has 3 balls. What is the total number of balls which he has? So this is the question over here, right? A chain of thought model will probably do what? It will first understand the information which it has in its hand, that is 5 baseballs, and now it has to do reasoning over here. So it will use its reasoning tokens to understand how it's meant to calculate this. How am I meant to calculate that he's buying 2 more cans and each can has 3 balls? So this is one specific information which is assigned to a token, right? And then this whole information is assigned to a token which itself generates reasoning tokens so that it can analyze and understand the problem and solve it, right? So this is obviously, there is one token over here where it has stored the information, and this information is linked to this one. So we get a final reasoning token based solution where it's doing the mathematical equation or the solving of the equation, which is what? 2 more cans with 3 balls. So 3 plus 3, which is equal to 6. Now it has to relate this information back to this information, because that's the final output which we require, right? Total number of balls, that is the output which we are trying to get. So this has to be linked two-way, and it has to add this value with the value which is linked to this token. So 6 plus 5, 11. Now let's understand this. If we just give the same question to Gemini over here, let's see how it will do it. I'm pretty sure it's going to do it the same way. Calculate ball number of cans. So, oh, nice. Peter buys 2 cans and each can has 3 balls. So the total is the total number of balls from the 2 cans is 2 into 3 balls per can. And then it is calculating that. Let's perform the calculation. Then it has given this 6 balls. Then it has given the final answer. Too much of text. With chain of draft, it will be something simple where let's take a different color to understand the chain of draft part over here. 5 balls. So this will be assigned to 1 token, right? And then this whole part will just be assigned to 1 token. No need for reasoning, because this is just simple arithmetic problem. And then this will just have 1 token assigned to it. So over here, instead of using reasoning tokens like we did over here, we are just using a simple token which will calculate this. So 2 more cans of 3 balls. So it's simple, 3 and 3. You don't need reasoning for this. And obviously, even for this question, you don't really need chain of thought reasoning. But to understand the advantage, we have to look at the thinking process itself. That is, the amount of tokens which are being used while getting to that answer is too much, right? Now, obviously, there are certain advantages of chain of thought. We have been telling that, chain of draft is better, chain of draft is this, that. Let's first understand the actual advantages of chain of thought. One is obviously improved accuracy, because it's going to reason, and it's essentially self-thinking. That's what thinking aloud means. In a certain paper, if you have read the Claude's reasoning paper, I'll provide a link to that also, and I'll maybe make a video on that. They basically talk, or they say in that paper, that models are actually not reasoning, but they already have a predefined answer. They have a predefined answer where they are just verifying it with their recursive thinking process. So let's say I have asked a question. It will have a self-generated answer, or it will have a generated answer already at hand. This generated answer is just doing cross checks with these reasoning tokens to basically give itself the confidence that, hey, I am right. So let's take this question only for example. It will probably know that it's 11 balls by just looking at the question. It will probably know it's 11 balls, but it's not confident. It wants to get more confidence by using these reasoning tokens. So let's say if it's giving out this output with 70% of confidence, these two reasoning tokens working together are basically praising it and saying that, hey, you're right. So that is boosting its confidence to, like, let's say 98%, and then it's giving the final output. So obviously the accuracy is still improved, even though it's using up a lot of tokens. That reasoning itself is allowing it to give a better answer. And when you're obviously doing a very compute intensive task, or something which is pretty complex, not simple questions like this, chain of thought obviously does better. So improved accuracy and interpretability. Interpretability is something which is used a lot in the field of ML, and that is basically the generated chain of thoughts. Let's basically make a chain, right? Let's make a chain over here and one more over here. Let's change the color of these to yellow so that we understand that this is the thought process. And then final, we'll have a green box which tells us that this is the answer. So let's say we have asked a question over here. Now, these steps are the chain of thought, where it's going like this. And then finally, the output is coming. So over here, reasoning is being done with a question like, why? So let's say if we take the understanding from the Claude paper, where a pre-generated answer is already there, the reasoning token is asking, why is this correct? So it's asking for a reason for why you think this answer is correct. And it's probably going to provide an answer, and that is going to get sent to this token, this stream of token, or this attention window. And over here, the reasoning token might question it further by saying why it can't be this. It might provide like a alternative solution saying that if you're saying it's 11, why can't it be 10? So it has to prove again that it's 11 because of this. And then this reasoning token might probably even not be used, or like it will just skip to this, or if it gets used, it might be for something very similar to this process itself. And then finally the answer is 11. This is the correct answer, and this can be sent to the user over here, who's all happy that he has gotten an answer to this very simple question. So this is how a chain of thought architecture in a very simple way would look like. And this is what makes it more interpretable, because you can see how it arrived to this answer. Like over here, we can see that how it's arriving to this answer. Although the output is over here, we can see what is the thinking process of the model. But the weakness is obviously there. That is, these step-by-step explanation, they can be very winded, or they can be very long. let's take an example which I faced with Grok. Okay, so I actually went through my chat history, but I was unable to find the actual chat which I had. I guess it's gone because I guess Grok has a limit of how many chat history it can store. So I use the think, uh, the toggle to let the model think, and I think I asked it something similar like, what is 3 to the power of 9, right? So over here we can see that, yeah, okay. So over here we can see that it's doing so much. Like over here it did first 3 into 3 into 3 9 times, then it did this bracket expression, then it did that again. It did, so it thought for 25 seconds today. The day I actually tried it, I think it thought for like 3 4 minutes. Like over here you can see that it started doing this standard multiplication method, then it started doing this. Like it's exploring so many pathways. This is actually called uh, multiple chain of thought. So what's actually happening is, oops, not that. What's actually happening is, let's assume this is the architecture diagram over here, and let's just go over here. Yeah, okay. So let's just go over here. What's actually happening is these and this. It's creating more reasoning tokens to explore multiple pathways. Like like we saw over there, it was doing normal multiplication, and it was doing what else was it doing? It was doing this standard multiplication method, and then it was doing in brackets, like so many methods. It's experimenting to essentially ensure that the answer which I'm getting is correct. Like over here, it probably got the answer, but it realized that it's too tedious and error prone. But it used up tokens to actually get to this point. Then again over here, but wait, raising to the power 3 means 27 into 27. That seems a bit cumbersome. Maybe I can find another way. So many reasoning tokens are being used for this simple task. This is where chain of draft comes in, where simpler tasks are going to just be straightforward, and that's the efficiency which they're talking about over here with their data accuracy and token count. We can see that standard obviously uses the least, but these are certain test cases which they tested on, and we can see that in sports, chain of thought had lesser accuracy, and chain of draft had more accuracy. In the token count, we can see that in date-based prompts, sports-based prompts, chain of thoughts is using like around 150, 170 tokens, whereas chain of draft is probably using around 20 to 30. Right, so we can see a very massive um, advantage of chain of draft itself. Another thing which they mention about in the paper is uh, common sense reasoning. Common sense reasoning is basically, let's take example of us humans again, because we as a superior species are have prefrontal cortexes and everything, and we can reason well, right? I'll take the example which I took in the last video with the light switches, light and fan switches. I'll make it very brief so that it's understood very quickly. Like, let's say I have a row over here. Okay, this is the switchboard. I turn on this, I click on this, and I see with my eyes, like I'm over here with as a person, and I see with my eyes that a light has turned on. So I can probably assume with some common sense that all these are light switches. No human is going to make light like that. And then let's say to double confirm, I might turn on this light, and I see that another light has turned on. And then to basically disprove my theory, what I might do is turn this light on or turn this switch on basically, and this might turn on the fan. very nicely drawn fan. This might turn on the fan, and to confirm my theory, I might switch this button, I might turn this button, and another fan might turn on, and I can now assume that this whole row is for lights, and this whole row is for fan. This is common sense reasoning. A model is not going to be able to do this. It will probably have to turn on all the light switches, then turn on all these fan switches to understand that, oh, this is for lights and this is for fan. Us as humans, we are above this. So over here, this is what they're talking about with their common sense reasoning. They talk about some data and symbolic reasoning. This is where they talk about the coin flipping task. So in symbolic reasoning, like I was saying, symbolic reasoning, right? Symbolic reasoning is basically us as humans. That is, like let's say we are trying to build a symbolic reasoning system, right? We as humans must learn the rules. We must learn the rules by which certain phenomena might relate, and then we will have to hard code those relationships into a static program. This is how a very small, obviously, symbolic reasoning system would be made. So usually they are represented via something called semantics. Okay, let me not write semantics. So for example, basically, let's say in Google, whenever you make a search, right, the top box which comes as the recommendation, it uses these semantics relationships, where it's going to give you the most search result, right? So when you say, let's say, the capital of Germany, and sometimes it will just show the answer right away as Berlin, instead of making you search on Google. This is what it's basically doing over here. The semantic relationship is being written over here. They are essentially a pile of like if-then statements. So where they are drawing the conclusion about certain entities. This relationship is defined by human intervention. So like let's say these semantics are written in, like, X is to Y, where X is a man and Y might be something like lives in India, right? So these two semantics are related and they have a relationship together. So let's say if you were to search on Google for something, you'll get queries or results based on that. This is what they're doing over here as well. They are noticing that in these concepts, in where there are semantics, chain of draft performs better. But obviously they also talk about certain limitations, and that is one major limitation which they talk about is inconsistency without few short examples. What they're saying over here is, let's go on a fresh slide. What they're saying over here is, let's assume this is the data set over here, okay, and we have lots of data filled. Chain of draft is basically in its system prompt, or it's in its system instruction. We can maybe see it in the code over here. Okay, I think it's in the configs. Yeah. So over here, they have given certain drafts for it to understand. Like, hey, if I get this type of prompt given to me, I need to create these drafts. So this is a work on top of chain of thought, but instead of creating those long streams of text, we are now just creating very short summaries. So let's say I have asked it a question. It'll just create a jotted down note, like how we do it in class. Like, you know, you're not going to write every single thing a teacher might say. You will just note down the key points, or like, you know, key topics for a upcoming exam. You'll note those down rather than the questions. You'll note down in DSA, you might note down linked list and queues. You'll not note down certain questions which are related to linked list and which are related to queues, because you don't know if they are going to come or not. You'll just note down that the important topics are linked list and queues. This is what chain of draft over here does. And this is where the limitation also comes in. Because in the code over here, they have given the examples. In all the code over here, they have given that, hey, this is how I want you to give the answer to me. They give the output style, that is, this is the question, right? And this is the answer which you have to basically draft to yourself instead of creating that huge stream of text. These are the two drafts which you just require. And then finally end the answer with these hashtags, and then the final answer which is there, that is yes. Okay. In chain of thought, obviously it will create that whole thought boxes and reasoning tokens, and then it will come to the final conclusion. The problem is they have to give these few short examples for it to understand the data, because the data sets are not made with these drafts. So the architecture over here struggles because those examples are not there. The examples are what? Huge bulks of text which are filled with information. When it's filled with information, the model will have to do what? It will first have to create the drafts and then use those drafts to reason and then give the final answer. So this is just even worse than chain of thought, where it's just reasoning and it's giving you the answer, right? Those drafts have been introduced with few short examples, and that's a limitation which it struggles with. Another limitation which it struggles with is performance on smaller models. So smaller models like 1.5 billion parameters or 3 billion parameters, they're trained with smaller data so that they can be run on everyday systems. That is where chain of thought over here, we can see it's excelling a lot. Almost the 3.23 billion instruct is destroying chain of draft model over here. It has used more tokens, yes, but the accuracy is making up for the lack which is there in chain of draft. Same over here for the Zoom SLM 2.3 billion parameter model. It has used 129 tokens, but it's also giving an accuracy of 77%, whereas it's just giving 50% while using 55 tokens. So what can we basically understand from this whole paper is that the concept is there. Like obviously a chain of thought prompting is good, and it has lots of scope, but it lacks in two major fields, and those two major fields are very important. One is inconsistency without few short examples, that is, it doesn't have data to work with for those drafts, and obviously reduced performance on small models. Since the main aim of these large language models is to be able to run on device, we need a prompting algorithm which is able to do those reasoning tasks and do them effectively, right? So if these chain of draft models aren't able to create effective drafts, then it's better to go with chain of thought prompts, and that's or chain of thought architecture, and that's what the paper essentially says at the end. COD demonstrates that effective reasoning in LLMs do not necessarily require lengthy outputs, and they're offering a alternative approach. And they're saying that if you pair COD with other latency reducing methods, like parallel reasoning or multipass validation, you could possibly get even more gains. Or something which you might consider in the future is training models with compact reasoning data, or basically giving them those small drafts so that they can understand that, okay, this is how drafts are created, this is how I need to generate them while reasoning. So this was the paper itself, obviously, and this is the code over here, where they have the simple model. Over here they are using Anthropic and OpenAI. They have compared a Claude 3.5 Sonnet model and I think GPT's model. These are all the chain of, this is the chain of thought system prompt, and this is the chain of draft system prompt over here. So this is the baseline one, right? This was the chain of draft and this was the chain of thought. You can see that it's more. So this is where the video comes to an end. I'd like to update this papers to read note which I had over here. I'll update it with a few more papers which I found while doing my literature study for this video. Something which I should have talked about but I didn't have time, I'll maybe touch up upon it briefly, is tree of thoughts. Okay, tree of thoughts. There's also something, if you just search up tree of thoughts, it's probably going to be the first paper, but I'll just write, it's by Shunyu Yao. Shunyu Yao. And then another one is, if you want to, like, get into these thought based prompting techniques, then there's another one called Skeleton of Thought, where they talk about parallel decoding. This is by Sufei Ning. And another one is, this is one of my favorite papers of all time, and I might just give it a separate note just for that. It is training large models to reason in a continuous latent space. Training LLMs to reason in a continuous latent space. I feel that these are very good papers to understand how these models actually reason and how their architectures work. And this is just a very brief example of how chain of draft works with visual examples over here and over here. But if you want to get to the nitty-gritty of how actually chain of thought works, then I would recommend obviously reading about chain of thought, and it's a very good paper in itself, and it's something which is currently being used in all the models right now. So yeah, I think it's a good it's a very good way to do reasoning. Now let's touch upon tree of thoughts, and for that we'll use a dark green color because trees. So basically over here, tree of thoughts is, if I can draw a diagram, let's take a circle. Let's say we have a input over here. We have given an input. Let me just zoom in. We have given an input. We have given an input. What it's going to do is, it will create multiple pathways which it can follow, similar to a tree in data structures. We know how simple trees work in data structures, right? It's for decision making processes and everything. This is how this is essentially how it does it for this reasoning also. So it will create these boxes for reasoning, where it will ask all of them to explore their reasoning logic in their own time and space. And finally, let's say this is the start, and it's like exploring of path, right? And the main aim is to get to the final output in the shortest path possible. So the model might take something like, if it takes this, it might reach a dead end. If it takes this path, it might reach a dead end. If it takes this path, it might lead to another box for reasoning. Then it might lead to the output. Who knows, if it takes this path, it might lead right to the output. But there's a chance that this might be wrong or this can be right. So the model has to make a decision whether it wants to go with this route where it's getting that extra clarity, or whether it wants to take the shortest path possible. This is how tree of thought prompting basically works. So it's essentially like the data structure trees, where it's used for decision making process, where it's exploring them, and then finally it comes to the output, and you get the output in token streams, and that is streamed to the model, and that comes out as your final word output which you get. So yeah, I hope you enjoyed this video. I don't think this is a longer video than the previous one, but I do hope you enjoyed it, and feel free to let me know what other papers I should do explanations on. So yeah, thank you for watching. Stay awesome and keep building something cool, and stay safe and take care, because I don't want to get too political, because recent news in India and the recent news between India and Pakistan is a bit scary time. So I pray for the families and the soldiers who are there at the border fighting for us, and also for the families who are there in those affected areas. I hope you're all I hope you're all safe and taking the necessary precautions. So yeah, take care. Bye bye.